All right, Math 5500. A couple of from the previous video, a few matrices that I actually intended to create in it, but I just magically just glossed right over it. I will uh, get those in this video. And I mean, it doesn't get much easier than creating these three. So anyway, let's move on to the variance covariance structure of betas, which is really going to be helpful for once we move into inference for using matrix operations. So what's the variance of our beta look like? Well, as a sidebar from a previous video, we saw that this very important product of the x transpose x, the inverse, looks like this. So the variance covariance matrix of the variances of our betas is going to look like this. So think again of beta 0, beta 1, and beta 0, beta 1. So on the diagonals, we'll have the variance of our beta 0 and beta 1, and on the off diagonal, we'll have the covariance between beta 0 and beta 1. And if I do my job correctly, if I can do my job correctly, you'll not only know how to, well, you'll not only see some of the underlying theory, you'll also see it at work in R, and hopefully I can explain to you what all this really means after all the smoke clears and dust settles. So we're going to calculate this by taking the variance times the product of this matrix. I wrote it all out because I didn't, mainly because I didn't want to write this out while on screen. And so it follows that the variance of B would be equal to just distributing the sigma squared through the terms. So our estimate is going to be sample variance of B, and we will replace sigma squared with the mean square error. So the variance covariance structure of our betas can be easily found by just taking the mean square error times this matrix. All right, so what I want to do now is I just want to move into R, demonstrate these four, and then come back and try to explain to you what all this stuff really means. So let's go into R, and you can see that I've already have the results from the previous video up. So let's dive in here. And first of all, I said we'd create the predicted values by taking our x times our, did I do uppercase case or lowercase? I always usually, as a rule, do name my matrices with capital letters. Okay, so that's one way of finding my predicted values. Another way is to take the hat matrix. So I'll be real clever here and just call it the predicted y with hat, or WH. And we know that we can take the hat matrix times our y. Well, our y in this case is looks like predicted y White House. So as it should, we get the same thing. And again, what I want you to see from this is that this H matrix, one of the properties of it, is it's a projection matrix. Again, it projects our observed y's onto the predicted y's. Now, if we want to find the errors using matrix operations, well, this is just going to be our y minus the design matrix times our beta. So our errors would be negative 3.32 and so on. Now, let's find our variance covariance structures. So again, we have a beta 0, beta 1, So we're expecting a 2 by 2 matrix. So I'm going to do the variance of B's. And so I need my mean square error. My mean square error is a constant, so I need to treat that as such with just a multiplication and not multiplying matrices. As well, don't want to use the 8 as I did up here. All right. So now I need my and we'll get a 2 by 2. Now, fine and dandy, right? We get our answer, 11.02 and 0.02 would be the variance for B0 and B1 respectively, and our covariance is negative 0.42. All right, cool. Now, what does this mean? Imagine this. All right, so we have this population model where we have our y's as beta 0 plus beta 1 x plus our errors. So what we do is we dive into this population and we take a sample. And from this sample, we are able to create our first estimate of beta 0 and our first estimate for beta 1. Now, let's assume we took another sample, sample 2. Because of sampling variability, we would expect our estimates for beta 0 and beta 1 to be different. Imagine doing this many times. So what we're going to have is we're going to have not only a distribution of sample intercepts, sample estimate intercepts, and a distribution of the estimates of the slope. These are estimates of each, right? We're also going to be able to extract ordered pairs. There's the first order pair. There's the second order pair, and so on and so forth. Now, on the variance covariance structure that we get from the previous, we know that these numbers have variation, and we can express that variation as looking at the variance or the standard deviation. So the variance of these beta 0, these estimates, is going to be this number right here, 11.02. The variance of our B1s, if we could just take all these numbers, and again, plug them into a calculator or whatever, and find the variance, the estimate of that variance is 0.0166. If we were to look at the covariance between these ordered pairs, the estimate of that covariance is going to be on the off diagonal. It's going to be negative. Negative just tells us as one goes up, the other goes down, right? Just exactly like with correlation. So again, this is the covariance estimate of beta 1, beta 0, beta 1, and this is the covariance of beta 1, beta 0. And again, because the covariance, we saw that the covariance of y sub I comma y sub j is the same thing as covariance of y sub j comma y sub I for all I not equal to j. We saw that in a previous video. We know that the off diagonals are going to create the same value. So I hope that brings a little clearer understanding about what's going on here. Now, it should go without saying, but if I needed the standard deviation for my beta 0, I'm just going to take the square root of 11.0158016, so 3.32. Which again, I mean, you think about once I dive into inference, if I want to find the confidence interval for beta 0, for example, I'm going to take the estimate plus or minus the t critical times the standard error. So the standard error doesn't use it uses the variance, but we'll need the standard deviation. So once we get to this point, we're going to need to take those diagonal elements and take the square root and create the standard deviation. Well, I believe that's all I got. I can't think of anything else I really want to add in this video. Moving on pretty soon to probably ANOVA. Matrix operations for ANOVA would be next. So take care.